Hello everybody, our project is evolutionary computation with Blackjack. For our project, our goal is to find the best strategy to the game of Blackjack using evolutionary computation strategies. Here is a brief introduction to Blackjack. The goal of the game is to beat the dealer without going over 21 points. Dealer must stop at 17 points. In this game, the basic operation includes hit and stand. Now, Ellen and I are going to show you how to play Blackjack.
So for the face values of the cards, if you have a normal card from 2 to 9, the face value is just the number on top of each card. If you have a face card like a jack, queen, or king, these have a value of 10. And if you have an ace, an ace could be either 1 point or 11 points. So ace could be a very powerful card. So we're gonna play a game right now. So at first, each player gets one card, and I'm the dealer, and Chin is the player over here. And each player gets one face down card and one face up card. And hit. Chin now has to decide whether to hit or stand.
Hit. Stand.
Stand. Okay, so Chin stands right now, and he has 9 plus 2 plus 10 points, which is 21. And the dealer has 20 points, which means the player wins this time. So in our project, we were writing a computer program to find the best Blackjack strategy. So we need a model for which the computer can make a decision on. So we came up with this table that models what these cards on a Blackjack table would look like. So on this column over here would have what the computer can see the dealer has, and up here you will have what the computer can see itself has in his hand. So for this cell over here, the computer has 0 aces, 0 cards between 2 and a 5, 0 cards between 6 and 9, and 0 cards between 10 and kings. And now I'm going to show you how the computer would use this matrix to play a game of Blackjack. I will be the dealer this time. So each person gets one face on and one face up. So the computer sees that the dealer has a 3, so that will correspond to the 3rd row on the table on the right. The computer sees that he has a king and one card between the range of 2 and 5. So according to the table, the computer will hit. So I'll give him another card. And now the computer would see that it has a king and 2 cards between the ranges 2 and 5. So the computer would hit again based on the table. And now the computer sees that it has 1 king and 3 cards between the range of 2 and 5. So according to this table, the computer would hit again. And now that the computer has over 21 points, it loses, so it wouldn't make any more decisions.
Now onto the genetic algorithm. This here basically outlines the strategy as to how it works. So first off, you'll be initializing your population, and then you'll enter a loop, and within that loop, you'll first score that population based on their fitness, so how well they solve that particular problem, which in our case is Blackjack. Then you're going to select the parents from that population. Then from those parents, you'll generate offspring, and those will be part of the next iteration's population. So it would be the next generation, essentially. You'll continue to follow that until all of those solutions seem to converge upon a single most optimal solution. So the 2 parent selection strategies that we chose to use in our implementation are mu plus lambda and mu comma lambda. The difference between the two is in mu plus lambda, both the parents and the offspring have a chance of moving on to the next generation, whereas in mu comma lambda, only the offspring are able to move to the next generation. Some of the potential trade-offs between using either of these different methods is when using just mu comma lambda, there is a chance that you could generate an optimal solution, one that is superior to others that do come, but you end up losing it because you do not save that parent which would have had that solution. Once your parents have been selected from the population, now it's time to generate the offspring, and there's a few ways that we can do that. So in this example of crossover, we select a single point along the strategy representation, and then from the left of that point, the strategy remains the same, and everything to the right is swapped between the 2 parents. This creates 2 new children that are both based off of those original parents, but provides 2 new solutions that can compete for fitness in the general population. So another way of introducing variation within this algorithm is by using something called mutation. And to do that, we select a random portion along a particular strategy and at random mutate or flip whatever current value is in that position in the strategy. So here you can see in the third index, instead of hit, we're just changing it to stand randomly. This is going to be something that adds variation and shouldn't be predictable in your algorithm.
A second method of evolutionary computation is called the particle swarm optimization. So in this method, it's also a repeated loop, just like the genetic algorithm. So the first step is to initialize your population, or in this case known as particles. While this loop is going on, you will calculate the velocity for each particle, which I'll explain later what that is. Then update the position of each particle until you reach a point of convergence. The velocity basically means the tendency of where these particles will move on into the next generation. So there are three determining factors that can influence a particle's velocity. One of the factors of velocity is the particle's previous velocity, shown in the red arrow over here. So that's where this particle got here before this current state. The second component of velocity is the history of the personal best solution this particle has experienced so far. A third component of velocity is this idea of the local best particle. So here you have a tendency for a particle to swarm towards the history of a local best particle. To determine what the local best particle is, there are two main methods that can be done. The first is known as the star topology. In this case, all the particles are interconnected, so each particle can have an influence on all the other particles. The second type of topology is the ring topology. In this case, each particle is only connected to two other particles. So when trying to find the local best particle, each particle will only influence itself and its two neighboring particles. And here is a visualization of how particles can swarm towards a good solution over time. So this particle swarm optimization continues to do these two steps: calculate the velocity and update the position based on the velocity until some convergence is met.
Here are some graphs to show the result of previous two algorithms. You can see the convergence of those two algorithms. Consider an evolutionary approach to develop more optimal solutions. I hope you enjoy this video.